Okay, it seems like we're ready. We're a few minutes late, but I think we can start. Welcome everyone for our Safari live seminar. I think this is the second one in October. I guess second one in the fall semester also. And we have Nastran Hajinazar, I think Dr. Nastran Hajinazar, who is going to present essentially the work that went into her PhD thesis, which she did in Safari. And these are two major pieces of work that she will discuss in detail. But Nastran essentially is a Safari member. She is still affiliated. She's working on research, but she did her PhD at Safari. She was an intern before she started her PhD at Safari. Actually, I think she spent quite some number of months in Pittsburgh and then went back to Vancouver and then came to Zurich and spent quite some number of months in Zurich also, and then went back to Vancouver. So she's truly a Safari member that has experienced multiple different locations of Safari. And she finished her PhD defense in June and submitted her thesis, which has the same title as this talk, at the end of August, if I remember correctly.
Sure.
Okay. With that, I think her thesis is titled "Data-Centric and Data-Aware Frameworks for Fundamentally Efficient Data Handling in Modern Computing Systems," and it looks into two major issues going into designing fundamentally better computing architectures. One is making them much more data-centric with the SimDRAM framework, and the other is making them much more data-aware with a rethinking of the virtual memory subsystem using the virtual block interface. And she's going to give an overview of both. And feel free to ask questions online or on Zoom, and she'd be happy to answer the questions. Okay, with that, please go ahead, Nastran.
Thank you so much, Indra, for the introduction. I'm going to start now. So yeah, as Indra mentioned, hi, first of all, my name is Nastran Hajinazar, and I will be presenting data-centric and data-aware frameworks for fundamentally efficient data handling in modern computing systems. Here's the outline for my talk today, and I will start by quickly going over the motivation and the problem that we're going to focus on today. As you know, modern computing systems need to process increasingly large amounts of data today. Many key applications and workloads of important wide range of domains are data intensive, and the potential improvement depends on fast and efficient processing of large amounts of data. With the advent of such applications, computing in modern systems is primarily bottlenecked by data. In other words, by how fast and efficient we are in accessing, moving, and processing data. Now, with the explosive growth of data, the important question is, do we handle data well in our computing systems? To answer this question, I will quickly discuss the major characteristics of modern computing architectures that make it significantly challenging to efficiently handle large amounts of data. The first of these two characteristics is processor-centric architectures. Now let's see what it means. A computing system has three key components: computation, storage and memory, and communication. Modern computing systems follow the processor-centric paradigm, in which computation is performed only in the processor, and every piece of data needs to be transferred to and from main memory to enable the computation. The processor-centric approach, as the predominant execution model used in almost all computing systems, is designed without having today's applications' overwhelming data demand in mind, causing significant waste in terms of energy and performance by requiring data movement across the entire system. This leads to data becoming a first-class concern and a prime performance and energy bottleneck in modern computing systems. The second key characteristics of modern systems that also impacts how we handle data is data oblivious policies, which we'll briefly discuss now. In addition to the growth in the size of the data that modern applications process, prior works show that different pieces of program data have different properties and different memory access behavior. It is shown that conveying this information to the hardware can enable vastly more intelligent data-aware management of the underlying hardware resources. However, the conventional virtual memory frameworks are designed without having many of today's computing systems and applications characteristics in mind, including the diversity in the properties of applications data. As a result, the existing virtual memory frameworks are not capable of conveying any insights regarding the properties and memory behavior of different pieces of program data. Instead, programs are traditionally conveyed to the hardware in the form of ISO instructions and a set of memory accesses to virtual addresses. This semantic gap leads to hardware treating all data as the same. Accordingly, the management and optimization policies used in existing systems are data oblivious and mainly component aware, which means that they're designed according to the characteristics of the component as opposed to the properties of the data that it handles. Data oblivious policies in modern systems are a direct result of how poor today's systems are in exploiting the valuable properties of different pieces of application data, which results in ineffective policies and lost performance optimization opportunities that can be achieved by exploiting data properties to improve the computing system's policies. We conclude that virtual memory as a critical component of the existing computing systems cannot effectively adopt modern applications data demand and data diversity, as well as all the changes that happen in today's systems in order to cater modern applications needs. We conclude that computation in modern systems is indeed bottlenecked by data and how today's modern systems and their key components are designed without having a large amount and diverse characteristics of modern applications data in mind. In this seminar, we discuss a set of approaches to fundamentally address the inefficiencies in handling the large amounts of data in today's computing systems.
Nasran, I think before you move on, I think your voice has become a bit worse. I think John mentioned that something is blocking your microphone.
Okay, I will make sure.
It sounds better to me. Is that correct for others?
Yes, sounds better to me now as well. So,
can you speak
again? There's
again?
a wire here that I moved. Maybe that helped.
So the microphone is attached to your computer, right? Not to your, I don't know, sweater or something. Is your hair blocking, for example, the
No, I'm using the laptop mic, so it shouldn't be anything. Yeah, there was just a wire here which I moved, and I'm hoping that that helps. Did it?
Yeah, I think it helped. I feel it helped, but
okay. I will make sure that I don't block it with my hand as well. Maybe that was an issue.
Okay, sounds good.
Okay, let me know if it's still not working. I will try to use my other mic. Okay. So should I continue?
Sure.
Great. So we basically argue that moving forward, computing systems need to consider data and the efficient computation of data as the ultimate priority of the system. In particular, modern computing systems should follow two main directions. First, in contrast to a processor-centric design, we argue that in order to efficiently handle large amounts of data, a system needs to be data-centric, meaning that it minimizes data movement and computes data where it makes sense, or in other words, where the data resides. And second, in contrast to data oblivious policies that I mentioned, we argue that modern computing systems should enable data-aware policies by allowing the software to easily communicate properties and semantic information about the application's data to the hardware. A data-aware architecture understands what it can do with and to each piece of data and makes use of different properties of data, such as locality and access semantics, to improve performance, efficiency, and other important metrics in the system. Accordingly, in this talk, we are going to discuss two key approaches for fundamentally efficient handling of data in modern computing systems. First, we present SimDRAM, an end-to-end processing using DRAM framework that aids the widespread adoption of processing using DRAM, a data-centric computation paradigm that improves the overall performance and efficiency of the system when computing large amounts of data by minimizing the cost of data movement and enabling computation where the data resides. To this end, SimDRAM efficiently computes complex operations required by modern data-intensive applications and provides the ability to implement new arbitrary operations as required. It also uses an in-DRAM massively parallel SIMD substrate that requires minimal changes to the DRAM architecture. Second, we introduced VBI, a data-aware, novel, and more scalable general-purpose virtual memory framework that enables efficient handling of large amounts of data in modern applications. VBI achieves this by efficiently understanding, conveying, and exploiting the properties of different pieces of program data to enable more intelligent management of main memory, efficiently and flexibly supporting increasingly diverse system configurations and memory architectures that are employed today to process the high data demand in modern applications, and providing the key features of the conventional virtual memory framework while eliminating its key inefficiencies when handling large amounts of data in modern applications. We now take a look at SimDRAM and efficient processing using DRAM framework as a data-centric solution. To begin, I will give a high-level summary of SimDRAM. Our primary motivation in this work is the increased interest in processing using memory architectures, which can efficiently perform bulk bitwise computations. However, current processing using memory architectures are not yet widely applicable, as they only support a limited and rigid set of operations, lack the flexibility to support new operations, and often require significant changes to the DRAM architecture. Accordingly, our goal in this work is to design a processing using DRAM framework that can efficiently implement complex in-DRAM operations, provide the flexibility to support new desired operations, and requires minimal modifications to the DRAM architectures. To this end, we introduced SimDRAM, an end-to-end processing using DRAM framework that provides the programming interface, the ISA, and the hardware support for efficiently computing complex operations, while providing the user with the ability to implement arbitrary operations as required. SimDRAM uses a massively parallel in-DRAM SIMD substrate that requires minimal changes to the DRAM architecture. Our evaluations show that SimDRAM provides 88 times and 5.8 times the throughput and 257 times and 31 times the energy efficiency of a baseline CPU and a high-end GPU respectively for 16 in-DRAM operations. SimDRAM also provides 21 times and 2.1 times the performance of a baseline CPU and a high-end GPU respectively for 7 real-world applications that we evaluate. Here is the outline for what we are going to cover about SimDRAM. I will start by briefly discussing processing using DRAM. To mitigate the costs of moving data between the computing units and memory, the processing in memory or PIM paradigm moves computation closer to where the data resides, reducing and in some cases eliminating the need to move data between memory and the processor. Processing using memory is one of the promising approaches to PIM, which exploits the analog operation principles of the memory circuitry to perform computation and benefits from the large internal bandwidth and parallelism available inside the memory arrays. A common approach for processing using memory architectures is to make use of bulk bitwise computation, as many widely used data-intensive applications such as databases, neural network, and graph analytics heavily rely on a broad set of simple logical operations and more complex operations. I will now give a brief background on how DRAM operates and how its operating principles can be used to build processing using DRAM architectures. A DRAM module is composed of many DRAM chips. Each DRAM chip contains several banks, and each bank has many subarrays, which are in fact two-dimensional arrays of DRAM cells. The DRAM cells in the subarray are horizontally connected using a word line and vertically connected using a bit line. The bit lines are connected to an array of sense amplifiers called row buffer. A DRAM cell is composed of a storage capacitor, which holds the value stored in the DRAM cell, and an access transistor, which enables and disables the charge flow from the storage capacitor to the bit line. DRAM cells operate using three main commands: activate, read, and write. Read, write, and pre-charge. To read the charge level stored in the storage capacitor, the memory controller uses an activate command. Once the DRAM array receives the activate command, the word line of the target row is raised, which connects all the cells along the row to the respective bit lines. As a result, the storage capacitor shares charge with its corresponding bit line and results in positive deviation of the bit line. Next, the sense amplifier is enabled, and the positive deviation in the bit line is sensed and amplified. Once the amplification is finished, the charge in the storage capacitor is fully restored, and the row buffer contains the value stored in the cell. The memory controller then issues read or write commands to the columns within the activated row. To prepare the DRAM array for future accesses, the memory controller issues a pre-charge command. To this end, first, the capacitor is disconnected from the bit line by disabling the word line. As a result, the bit line voltage is restored to its initial state. And finally, the sense amplifier is disabled. Now the DRAM array is ready to perform the next accesses. Now let's see how we can use this internal DRAM cell operation to perform in-DRAM computation. We start with performing in-DRAM row copy. Let's assume that we want to copy the value stored in source row A to the destination row B. The two rows share the same bit line. Row pool enables copying the source row A to the destination row B in the same subarray by issuing two consecutive activate commands to these two rows followed by a pre-charge command. First, an activate command is issued to source row A, which pulls the bit line to the value of the cells connected to them and copies the content of the source row A into the row buffer. The second activate command to the destination row B connects the cells in row B to their bit lines. Now, because the sense amplifiers have already sensed and amplified the value stored in the source row A, by the time that row B is activated, the data in each cell of row B is overwritten by the data stored in the row buffer, copying the data in the source row A to the destination row B. Finally, the pre-charge command prepares the DRAM array for the next memory accesses. We can follow a similar principle to execute majority functions in DRAM. To refresh your memory, the output of the majority function is 1 only if more than half of its inputs are 1. Let's assume we want to compute the majority of the values stored in the three rows of A, B, and C. Ambit, a prior processing using DRAM architecture, shows that simultaneously activating three DRAM rows using a DRAM operation called triple row activation can be used to perform bitwise majority operations on the values stored in the cells of the three rows. Let's see how it works. First, activating all three rows simultaneously results in a positive deviation of the bit line. After sense amplification, the sense amplifier drives the bit line to VDD, which is the majority of the values stored in the three cells in this example. The cells are then fully charged because of the amplified voltage of the bit line. In other words, all three DRAM cells are overwritten by the result of the majority operation. At the end of the operation, a pre-charge command is issued to prepare the DRAM array for future accesses. Ambit uses the triple row activation command sequence to implement Boolean and OR operations by simply setting one of the inputs, for example, C in this example, to 1 or 0, respectively. The AND operation is performed by setting C to 0, and the OR operation is performed by setting C to 1. In order to perform processing using DRAM, Ambit splits the DRAM rows in a subarray into three groups. Compute rows, which can execute triple row activation. Two control rows that are pre-initialized with all ones and all zeros and are used to control performing AND or operations during a triple row activation.
Hi, Nestor, I think your voice is fading.
Oh, that's sad. Let me see.
Yeah. If you have another microphone, that might be.
That may take a minute. Is that okay?
I think so. If it's significantly better, I think, because you may run into this problem again.
Yeah, let's try it. It is worth trying. Just a sec. I will stop sharing the screen for a sec. I'll be back.
In the meantime, maybe people can think of questions. We cannot hear you now.
Okay, how about now?
This sounded much better.
Okay, sorry for the delay.
Yeah, we should have started with this one perhaps, but hopefully it'll stay this way. Okay.
Yeah, hopefully. Yeah, so where were we? Yeah, so as I was saying, Ambit requires only minimal modifications to the DRAM subarray. More
You're not seeing your
specifically,
screen.
I'm not? Oh, okay.
I don't see it.
Okay. That is true. I guess that's where we were. Yeah, so as I was saying, Ambit requires only minimal modifications to the DRAM subarray. More specifically, while the regular row decoder is used to activate rows in the data and control groups, Ambit uses a small special row decoder for the compute rows to perform tuple row activation. The compute row decoder can simultaneously activate 3 rows using a single address, which is used to perform majority function on the values of the 3 activated rows. These modifications impose less than 1% area overhead in a commodity DRAM chip. Inspired by rowclone and Ambit, many prior works have explored DRAM designs as well as other memory technologies that are capable of performing computation using memory. However, they suffer from 3 major shortcomings. First, they support only basic operations and fall short on efficiently supporting more complex operations, which limits their applicability. Second, they support only a limited and specific set of operations, lacking the flexibility to support new operations and cater to the wide variety of applications that can potentially benefit from processing using DRAM. And finally, they often require significant changes to the DRAM subarray, which makes them costly. This highlights the need for a framework that aids the general adoption of processing using DRAM by efficiently implementing complex operations while providing the flexibility to support new desired operations. Accordingly, our goal in this work is to design a processing using memory framework that efficiently implements complex operations, provides the flexibility to support new desired operations, and minimally changes the DRAM architecture. I will now describe our proposed processing using DRAM framework called SimDRAM. SimDRAM is an end-to-end processing using DRAM framework that provides the programming interface, the ISA, and the hardware support for efficiently computing complex operations in DRAM and providing the ability to implement arbitrary operations as required. SimDRAM achieves this using an in-DRAM massively parallel SIMD substrate that requires minimal changes to the DRAM architecture. I will now describe the DRAM substrate that SimDRAM uses for in-DRAM computation. We built the SimDRAM framework around a DRAM substrate that enables two key techniques. First, vertical data layout in DRAM. Prior works showed that employing a vertical layout for the data in DRAM eliminates the need for adding extra logic in DRAM to implement bit shift operation, which is essential for many complex operations. Employing vertical data layout provides SimDRAM with two key benefits: implicit shift operation and massive parallelism, where each data DRAM column operates as a SIMD lane. The second key technique used in SimDRAM substrate is majority-based computation. As opposed to using basic logic operations such as AND, OR, and NOT to implement in-DRAM computation, SimDRAM uses logically complete set of majority and NOT operations to implement in-DRAM computation. Doing so enables SimDRAM to achieve higher performance, higher throughput, and lower energy consumption compared to using basic logic operations for in-DRAM computation. Now let's take a look at the SimDRAM framework. The SimDRAM framework is composed of three key steps. The first step of the framework builds an efficient majority NOT representation of a given desired operation from its AND or NOT-based implementation. The second step allocates DRAM rows to the operation's inputs and outputs and generates the required sequence of DRAM commands to execute the desired operation, which is called a microprogram. The third step executes the microprogram to perform the operation. SimDRAM uses a control unit in the memory controller that transparently issues the sequence of commands to DRAM as dictated by the microprogram. Now let's take a more detailed look into the first step of the SimDRAM framework. As Ambit showed, it is quite trivial to convert a Boolean equation to its equivalent majority equation, as each two-input AND operation can be implemented using a three-input majority operation where one of the inputs is tied to logic 0, and an OR operation is implemented using a three-input majority operation where one of the inputs is tied to logic 1. Accordingly, the first part of the transforming process in step 1 of the SimDRAM framework is simply replacing the AND and OR primitives with majority primitives in the logic representation of the desired operation. However, naively converting AND and OR primitives with majority results in an implementation of the operation that correctly replicates the functionality of the initial AND or NOT-based implementation, but is often inefficient. To address this issue, the second part of the transformation process takes the inefficient majority NOT-based implementation and uses a greedy optimization algorithm that applies a series of transformation rules to reduce the number of majority operations required to perform a desired operation. For example, this picture shows the generated majority NOT-based implementation to compute the carry propagation logic in a full addition, which requires only one majority operation instead of 4. Therefore, step 1 generates an optimized majority NOT implementation of the desired operations. Let's now take a more detailed look at step 2 of the SimDRAM framework. Each SimDRAM operation is stored in the memory as a microprogram, which actually is a series of DRAM commands, such as activation and precharge, that SimDRAM uses to execute operations in DRAM. Accordingly, the goal of the second step of the SimDRAM framework is to take optimized majority NOT-based implementation created in step 1 and generate a microprogram that executes the desired SimDRAM operation in DRAM. To this end, the second step performs two key tasks on the optimized majority-based implementation of the operation. First, it allocates DRAM rows to the operation's operands, and second, it generates a microprogram that performs the series of DRAM commands on the rows containing the operands that is required to perform the desired in-DRAM operation. Now let's take a look at the first task of step 2. The goal of task 1 is to allocate DRAM rows to the input operands of each majority primitive in the majority NOT-based implementation of the operation. When allocating DRAM rows to operands, SimDRAM takes into account two extra constraints that are specific to processing using DRAM. First, the number of compute rows reserved to perform bitwise operation is limited. And second, performing majority operations in DRAM has destructive behavior. In other words, as we saw earlier, the triple row activation operation overrides the original values of the three input rows with the output of the majority operation. Based on these two constraints, we present a new allocation algorithm inspired by the linear scan register allocation algorithm. Our allocation algorithm takes as input the majority not implementation of the operation generated in step 1 and starts by assigning the inputs of each majority logic primitive to the available compute rows one at a time. Since the number of compute rows are limited, this step of the algorithm assigns only as many inputs to the compute rows as the number of compute rows that are not allocated to any operand yet. Next, performing triple row activation in the compute rows, which in this example computes the majority of A, B, and carry in, which in fact computes the carry out value. As a result of the destructive behavior of the triple row activation in DRAM, the carryout is stored in all three input rows at the end of the triple row activation process. Our allocation algorithm takes advantage of this behavior and reuses these rows as inputs of the next majority operation in case the value stored in any of these rows is an input for the next majority operation. Now let's take a look at the second task of the step 2, which generates the microprogram to perform the desired in-DRAM computation. Task 2 works in 3 key parts. The first part generates an initial microprogram. This part first copies the 3 operands from the data rows to the compute rows allocated to them in task 1, using row copy operation, which, as we saw earlier, consists of 2 activations followed by a pre-charge. Once all inputs of the majority operation are copied to the allocated rows, a triple row activation is issued to execute the majority operation. Finally, another row copy is issued to copy the output of the majority operation that is stored in the compute row back to the destination data row. The resulting sequence of DRAM commands represents the initial microprogram. The second part of task 2 optimizes the initial microprogram by leveraging the structure of our processing using DRAM substrate, including the ability to coalesce multiple row copy operations into a single one and merging a majority and a row copy operation into a single operation. With these 2 optimizations, an optimized microprogram is generated that requires fewer DRAM commands to perform the same desired in-DRAM operation. I invite you to read our paper for more details about the 2 optimizations that I mentioned here. Once all potential operations are coalesced, the framework now has an optimized microprogram that computes the desired operation for operands of size 1 bit. The final part of task 2 generates this 1-bit version of the operation into an n-bit version by repeating the DRAM commands in the optimized microprogram for n times. The final outcome is an optimized microprogram that requires minimum number of DRAM commands to perform the desired in-DRAM operation on operands of size n. The final microprogram is then stored in a reserved region of DRAM for future use. Also, a new SimDRAM instruction called BBUp is created specifically for this new in-DRAM operation and added to the CPU ISA. The BB operation instruction is used later by the programmer to perform the added SimDRAM operation. Now let's take a look at step 3, the final step of the SimDRAM framework.
Nastaran.
Yeah.
Hello, this is Juan. I would like to ask you something about the previous step.
Sure.
So you start from the one of the constraints that you have from the start is the change, right? So
sorry, Juan, I cannot hear you properly. Can you please repeat, please?
Yeah. So can you hear me now?
Yeah, I do.
Okay. So yeah, my question is, there is a number of compute rows in the DRAM subarray that you can use for compute for the triple row activation, right?
Mm-hmm.
And that's one of the constraints that you take into account when designing task 1 and task 2 of a step 2, right?
Mm-hmm.
So how good these two tasks change if you also change the number of compute rows that you have, assuming that, for example, you can afford more area cost in these special row decoder that you presented. So do you think that these two tasks could be still valid the way they are? Would they change significantly, and would that have some later effect on the actual performance?
Mm-hmm. Very good question, actually. Thanks, Juan. So considering that task one is allocating DRAM rows to the operand and task to generate microprogram, the constraints, how the constraint affect these is that, for example, as I said, we assign as many operands to the DRAM rows as there are compute rows available, which means that we can, if we have more compute rows available for us, we can copy more operands if needed to the DRAM rows and have them available there, and not basically move data around between performing the DRAM, SimDRAM, sorry, the micro commands to perform the SimDRAM operation in order to complete the entire SimDRAM operation. So we'll move more operands in, and we'll just perform the majority and majority and not operations while the data resides in the compute rows, without having to have them move around between the data rows to compute rows and wait for that, basically. And the second impact is that basically we won't need to coalesce, we won't need to optimize anything for coalescing majority operations or not operations, and like there are more explanation of that in the paper. But the direct result would be not waiting to basically move data around. So for example, another example of not having to move data around other than moving inputs and outputs to the compute rows is that when there's intermediate data produced as the output of a majority operation, which is input to the next majority operation, not directly the next majority operation, we need to move it to the data row first in order to perform the next majority operation, which doesn't need that data, and then bring the data back in case that data is required for future majority operations. But if we have more compute rows available, we won't need to do that, and we'll keep the data in the compute rows. So it will basically impact the amount of data movement within the subarray, which has impact, direct impact on the power and also performance of the SimDRAM substrate positively. I hope that answers your question.
Yeah, I think so. Thank you very much, Nastaran.
Thanks for your question, Paul.
Hello, Nastaran, Geraldo here. So
Hi,
I have
Geraldo.
now that you are in this topic, I have a question also related to data being limited inside the subarray. You said that with these more compute rows, you'll move data less inside the subarray. What about if the size of the subarray itself is not enough? How could you move data? Would you need, or how could you move data across different subarrays if required, or across different banks, for example? And would that impact the performance of the SimDRAM operations, for example? Oops.
That's a great question, Geraldo. Thanks for asking. So SimDRAM operates on data placed with the same subarray, but a single subarray stores only several megabytes of data. For example, a subarray with 124 rows and a row of size 8 kilobytes can only store 8 megabytes of data. So as a result, SimDRAM would need to use a mechanism that can efficiently move data around within DRAM, as you mentioned. So SimDRAM can in this case would be able to exploit the row clone mechanism, which has a pipeline serial mode or PSM to copy data between two banks by using the internal DRAM bus. Or in other cases, it would be able to use the low-cost interlinked subarray or LISA mechanism that has published before to copy rows between two subarrays within the same bank. We actually evaluate the performance overheads of using these both mechanisms in the paper, and I invite everyone to look into the paper for more details about that. Does that answer your question?
Yes, thank you so much, Nastaran.
First, thanks for asking. Yeah, so let's take a look at the third step of the framework, which is the final step. Yeah, so SimDRAM uses a control unit in the memory controller that handles the execution of the microprogram at runtime, which happens transparently to the programmer. To perform a SimDRAM operation, program uses the appropriate BB operation instruction that refers to the target operation. Upon receiving the BB operation instruction, the control unit loads the microprogram corresponding to the BB operation from the main memory and performs the requested SimDRAM operation by issuing the sequence of DRAM commands stored in the micro-operation of that operation. At the end of the microprogram's execution, the outcome of the SimDRAM operation is stored in the memory. I invite you to read our paper for a detailed reference implementation and the microarchitecture of the SimDRAM control unit. Next, I will discuss the integration of the SimDRAM framework in the system. We employ several techniques.
Sorry, I have a question about the control unit that you just presented.
Sure.
Before you enter to system integration.
Mm-hmm.
So there are recently industry-related process memory solutions like Samsung SimDRAM, for example, that propose some ways of to offload computation to the process memory unit without changing the memory controller basic. Pretty much assuming, oh, your screen went off. Yes, great, it's back.
Okay, good.
Yes, pretty much just using whatever JDEC protocol DRAM uses, right? So would SimDRAM would be able to work if you don't change the memory controller? Like basically, how necessary is this control units to enable the programmability of the operations in SimDRAM? Can we go by without having this control unit, and what's the benefits that it provides?
So the reason that we need the control unit is basically to be able to make it transparent to the user, to put it simply. So what happens is that the user won't be involved in the DRAM commands such as activation or pre-charge that we perform to compute the majority and not operations required for SimDRAM substrate. That's why we have the interface implemented in the control unit, the user interface implemented in the control unit of SimDRAM. But if the user directly is able to issue DRAM commands that are required to perform the majority and not operations, we would not require any changes to the memory controllers, such as the same thing that FIMDRAM does. FIMDRAM basically issues DRAM commands somehow directly to the DRAM to perform the in-DRAM computation. So assuming that if we use the same programming model as they use, we would not require any changes to the memory controller as we do in this example implementation that is present in the paper. Does that answer your question?
Yes, thank you so much. And I have another question related to how you talk about a little bit about programming interface, right? And enabling computation to be done without intervention from the user. I guess right now how SimDRAM is implemented, we are not leveraging any metadata or any further information that the software could provide to the control unit or something like that. So would it be helpful to enhance this programming model with some more metadata or some hints to the programmer or to the control units to more efficiently execute SimDRAM operations?
That is a very good question. Yes, the answer is yes. So one example that I can think of immediately is, for example, something that is important in processing using DRAM or processing in memory in general is to reduce the amount of data movement, which is the motivation behind the entire paradigm. So one thing that would be very good to know prior to starting to compute in the DRAM is to know where the data should be in order to reduce the amount of data movement to basically put the operands together. So if you remember, I mentioned that the operands of a SimDRAM operation need to be in the same subarray, right? So prior to starting the computation, if we know what operands are required for each operations and which operations we are going to compute, basically, we can come up with a more optimized placement of data in the DRAM so that we reduce the amount of data movement that's required to perform the entire piece of computation that we're going to compute in the DRAM. So that is a simple and direct example of how metadata And basically knowing the behavior of the application prior to starting the computation in the DRAM would help us. And there are many other examples, but yeah, definitely knowing more about the application behavior enables us for making more intelligent decisions in terms of computation in general. Computation in memory is an example. I will cover how knowing more information about the application behavior would enable us for making more intelligent decisions in the second part of my talk.
Great.
Yeah.
Thank you so much, Nasser.
Yeah, thanks for the great question. Yeah. So in SimDRAM, we employ several techniques to efficiently integrate SimDRAM in the system. The first technique is regarding efficient transposing of the data layout in DRAM that enables SimDRAM to store the data required for in-DRAM computation in the vertical layout. So while SimDRAM operates on vertically laid out data, the other system components, including the CPU, expects the data to be laid out in the traditional horizontal format, making it challenging to share data between SimDRAM and the CPU. To address this issue, SimDRAM uses a specialized hardware unit placed between the last level cache and the memory controller called the data transposition unit to transform the data layout from horizontal to vertical and vice versa. The transposition unit tracks SimDRAM objects or data objects used in SimDRAM operations and ensures that their data is stored in the vertical layout and ready for SimDRAM computation whenever data is present in DRAM, and in the horizontal layout whenever the data is present in the cache so that it is ready for computation in the processor. Our evaluations show that the transposition unit imposes very low overhead on the throughput of SimDRAM operation, while imposing very low area overhead in commodity DRAM chips. I invite you to read our paper for more details about the transposition unit and the rest of the SimDRAM system integration techniques, such as the programming interface of SimDRAM, how SimDRAM handles page faults, address translation, coherence, and interrupts, or how SimDRAM manages computation on large amounts of data, security implications of SimDRAM, and also the current limitations of the SimDRAM framework. I will now present the results of our evaluations for SimDRAM. We implement SimDRAM using Gen 5 simulator. We compare SimDRAM against 3 baselines: a multi-core CPU, a high-end GPU, and an Ambit, which is a state-of-the-art in DRAM computing mechanism. We evaluate 3 different configurations of SimDRAM. One bank configuration, where a single DRAM bank out of the 16 banks is extended to enable SimDRAM computation. This enables SimDRAM to execute operations over 64,000 SIMD lanes. We also evaluate SimDRAM with 4 SimDRAM-enabled banks and 16 SimDRAM-enabled banks as the third configuration of SimDRAM. To demonstrate its generality, we evaluate SimDRAM using 16 complex in-DRAM operations and 7 commonly used real-world applications from various domains. First, we compare the throughput across all 16 SimDRAM operations. Here, the x-axis shows each one of the 3 baselines that we evaluate, and the y-axis shows the average throughput in giga-operations per second normalized to the corresponding baseline. We make 3 observations here. First, SimDRAM with a single bank provides 5.5 times the throughput of the baseline CPU, and this value increases to 22 times the throughput of the baseline CPU using 4 DRAM banks and to 88 times using 16 DRAM banks for in-DRAM computation. Second, SimDRAM with a single bank is not enough to outperform the throughput of the GPU. However, with 4 DRAM banks, SimDRAM provides 1.5 times the throughput of the GPU, which scales to 5.8 times when using 16 DRAM banks. Third, compared to Ambit, SimDRAM with a single bank provides 2 times the throughput of Ambit, while SimDRAM with 4 banks provides 7.9 times, and SimDRAM with 16 banks provides 31.6 times the throughput of Ambit. We conclude that SimDRAM can largely outperform all 3 state-of-the-art baselines for a wide range of operations. We also evaluate the energy efficiency of SimDRAM across all 16 operations that I mentioned. Here, the x-axis shows each one of the 3 baselines, and the y-axis shows the average energy efficiency in throughput per watt normalized to the corresponding baseline. We make the following observations. SimDRAM provides 257 times the energy efficiency of the CPU baseline, 31 times the energy efficiency of the high-end GPU and 2.6 times the energy efficiency of Ambit. We conclude that SimDRAM is more energy efficient than all state-of-the-art baselines. Finally, we compared the speed-up that SimDRAM provides across all 7 commonly used real-world applications. Here, the x-axis shows each one of the 3 baselines that we evaluate, and the y-axis shows the average throughput normalized to the corresponding baseline. We make 3 observations here. First, SimDRAM with a single bank provides 3 times the speedup of the baseline CPU, which scales to 8.7 times using 4 DRAM banks and 21 times using all 16 banks for in-DRAM computation. Second, SimDRAM with a single bank and with 4 banks is not enough to outperform the GPU. However, by using all 16 SimDRAM-enabled banks, SimDRAM provides 2.1 times the speedup of the GPU on average across all 7 applications. Third, SimDRAM with a single bank provides 2.5 times speedup compared to Ambit, which scales to 7.3 times using 4 DRAM banks and 17.5 times using all 16 SimDRAM lanes for in-DRAM computation. We conclude that SimDRAM can effectively and efficiently accelerate many commonly used real-world applications. I invite you to read our paper for more details and more evaluations, such as the reliability of SimDRAM operations, the overhead of transposing data layout, the area overhead of the SimDRAM framework, SimDRAM performance and energy benefits over a closely related processing using cache architecture, and more. Now let me conclude. Go ahead.
Before you conclude, you have some question from YouTube
Sure.
Related to system integration, actually. Someone is asking if transparent to the programmer means that the major control is shifted to the compiler. So what does we mean by transparent to the programmer? And is there any relation to the compiler? Like how you, for example, implement those real workloads in SimDRAM? Like, does SimDRAM have a compiler?
So we basically would require a compiler basically to convey the SimDRAM operations to this control unit of the SimDRAM, but the rest of it is transparent because it is taken care of in the control unit of the SimDRAM. By transparent, I mean that the transposition is transparent to the programmer. The programmer would at no point in the process would know that the data is stored in vertical or horizontal layout. Or the programmer doesn't need to worry about which DRAM command needs to be issued or any of those details, which would basically make this framework much more difficult to be used. So that's what I mean by transparent. These are happening transparently to the user, and most of these tasks are done in the control unit of the SimDRAM.
So just to clarify, then we don't propose a compiler. Then so we have some ISA instructions as you presented in the as output of the second step, right? And from those ISAs, which are those instructions that are make available to the user, I guess, rewrite the application, and then it's just as an API call, right? To anything, and this API call or this instruction is encapsulating, transposing data or issuing activations or pre-charge comments to the computation, and so on. If I understood correctly, right?
Yeah, that was actually correct. So basically, what I meant is that we don't need anything extra from compiler than any other regular instruction for SimDRAM.
Yes, thank you so much. And I have a question myself about SimDRAM. Like, you are proposing this general framework, right, to do complex operation in DRAM. Like, how general is this? Like, can we implement any instructions that I want in DRAM, or is there some current limitations?
Well, why SimDRAM is flexible to implement any operation? It is mainly well suited to applications that are SIMD friendly and have a regular access pattern and are memory bound. Basically, these 3 characteristics will make applications very good candidates for substrates such as SimDRAM, any in-memory computation substrate, for example, SimDRAM. And such applications are common in domains such as databases or database analytics, basically, or high performance computing or image processing and machine learning, which covers important domains of applications. But again, SimDRAM is the first computing using DRAM framework that makes it absolutely possible to implement any desired operation by the user, which is easily being, like, it's able to easily add that operation to the set of operations that it's capable of performing. This is basically what makes SimDRAM different than the prior processing using DRAM substrate.
That's right. And a last question from me from this part. How realistic do you think that SimDRAM is to be implemented in a real system? Like, is there any prior work that, for example, shows that DRAM is capable of doing this majority operation, which is the basis of SimDRAM? And do you think SimDRAM would cope well to this type of system if they exist, actually?
Yeah, so there's this prior work called Compute DRAM, which shows how ambit is possible in commodity DRAM chips that are already available commercially, right? And so Compute DRAM shows that ambit is possible, and SimDRAM does not require anything in any changes in the subarray organization on top of what ambit needs, which makes us a solution that would also be able to implement, would also be a good candidate to be implemented in DRAM, and basically implemented in the DRAM and employed by the users without any extra changes in ambit. And yeah, Compute DRAM as a prior work shows that this is feasible. Does that answer your question?
Yeah, I think that is great. If there is a prior work that shows that it's feasible in real DRAM, I think, yeah, there is no reason for SimDRAM not being applicable, right? And probably this is a really good future work that someone that wants to, because you said that SimDRAM was done in Gen 5, right, in simulation. Yeah. So maybe someone can connect the dots and do like a prototype of the system there with real DRAMs, maybe. But thank you so much. Those are my questions, Master.
Of course. Where were we? Yeah.
You're about to conclude.
Yes. So in conclusion for the SimDRAM part of my presentation, we introduced SimDRAM, an end-to-end processing using DRAM framework that provides the programming interface, the ISA, and the hardware support for efficiently computing complex operations while providing the user with the ability to implement arbitrary operations as required using a massively parallel in DRAM SimD substrate. And as I mentioned, our evaluations show that SimDRAM provides 88 times and 5.8 times the throughput and 257 times and 31 times the energy efficiency of a baseline CPU and a high-end GPU respectively for 16 in DRAM operations, and 21 times and 2.1 times the performance of a baseline CPU and a high-end GPU respectively for 7 real-world applications. We conclude that SimDRAM is a promising We conclude that SimDRAM is a promising processing using memory framework that can ease the adoption of processing using DRAM architectures and improve the performance and efficiency of processing using DRAM architectures. Now that we have covered our first proposed approach for data-centric approach for handling large amounts of data in modern applications efficiently, we'll move to take a look at the next approach called VBI, which is a data over novel virtual memory framework. To begin, I will give a high-level summary of the VBI part of my presentation. The motivation of this work is that modern computing systems continue to diversify with respect to system architectures, emerging memory technologies, and applications memory needs. Unfortunately, continually adapting the conventional virtual memory framework to each possible system configuration is challenging and often results in performance loss or requires non-trivial workarounds. Our goal in this work is to design an alternative virtual memory framework that efficiently supports a wide variety of new system configurations and provides the key features of the conventional virtual memory framework while eliminating its key inefficiencies. To this end, we propose Virtual Block Interface, a novel alternative virtual memory framework that delegates the physical memory management to a dedicated hardware in the memory controller. VBI efficiently adapts to different and increasingly diverse system configurations. It also reduces the overheads and complexities related to the conventional virtual memory framework. The memory controller-based memory management in VBI leads to many benefits, some not easily attainable in existing virtual memory frameworks, such as low overhead page walks in virtual machines and inherent virtual caches. We demonstrate the benefits of VBI with two concrete use cases. First, we experimentally show that VBI significantly improves performance for both native execution and virtual machine environments by 2.4 times and 4.3 times respectively. Second, we show that VBI significantly improves the effectiveness of heterogeneous main memory architectures. Here's the outline of what we are going to cover regarding VBI. I will first explain our motivation for this work. Virtual memory is a core component of modern computing systems. The virtual memory model has remained mainly the same since its inception and was originally designed for systems whose memory hierarchy fits a simple two-level model of a small but fast main memory and a large but slow external storage. In such a configuration, the OS can easily abstract away the underlying memory architecture details and present applications with a unified view of memory. However, modern applications and computing systems no longer follow this model and continue to diversify significantly. For example, with respect to diverse and high memory requirements of modern applications and properties of different pieces of their data, new system architectures and emerging memory architectures and technologies that we use today to cater to the high memory demand in modern applications. Therefore, the OS must now efficiently satisfy significantly higher memory requirements and diverse data characteristics of modern applications that leverage the advantages offered by emerging memory architectures and new system designs, while simultaneously hiding the increasing complexity of the underlying memory and system architectures from the application. Unfortunately, this is not an easy problem to tackle in a generalized manner and often results in performance loss or requires non-trivial workarounds. As a result, continuing to adapt the conventional virtual memory framework to today's application data demand and diverse system configurations is not easy. Before diving into these challenges, let's take a look at the conventional virtual memory design. This figure illustrates the virtual memory management in Intel x86 as an example of a conventional virtual memory framework. In such a framework, each process is mapped to a single private virtual address space of fixed size, for example, 256 terabytes in Intel x86. The operating system controls the access permissions by managing the one-to-one mapping of processes to their specific virtual address space. And the OS defines the mapping from each process's virtual address space to the physical memory and stores both the mapping information as well as permission information in a set of per-process page tables. The page tables are managed by the operating system and read by the memory management unit in the processor to perform address translation. This design suffers from many fundamental challenges when adapting to modern applications' higher data demand and modern and diverse system configurations. Here we have three examples of such challenges. The first example is related to the flexibility of the conventional virtual memory framework in adapting to the modern application's memory requirements. Prior works show that many applications can reduce the address translation overhead using flexible page tables that are customized to the application's actual memory footprint and access pattern. However, in conventional virtual memory framework, as I said, while the OS defines the virtual to physical address mapping in the page tables, the hardware still needs to read these tables to perform address translation. This arrangement requires rigid address translation structures that are shared between and understood by both the hardware and the OS. For example, the 4-level page table of fixed granularity in Intel x86. And as a result, implementing such flexibility in the page table that enables application to benefit from their different characteristics of the different pieces of data would be very challenging due to the rigidity of the conventional virtual memory design. Another challenge exists when adapting the conventional virtual memory framework to virtualized environments. In virtualized environments, the guest OS is running on top of the host OS in a virtual machine, which in such a setting, the guest OS, unaware that it is running in a virtual machine, performs memory management on the emulated physical memory and translates the guest virtual address to the guest physical address, which is in fact the host virtual address. The host OS then performs a second round of memory management, mapping the host virtual address to the host physical address. This extra level of interaction results in many important issues, including two-dimensional page walks where the number of memory accesses required to perform address translation increases dramatically. This issue makes it challenging to perform computation in virtualized environments efficiently. The third challenge that we discuss here arises when managing heterogeneous memory architectures. Enhancing performance with heterogeneous memories requires first dynamically mapping data to different physical memory regions according to applications requirements. For example, mapping frequently accessed data to fast memory. And second, migrating data when those requirements change. Since in conventional virtual memory frameworks, the OS defines and manages the address mapping, efficiently implementing such functionality faces the fundamental issue that the OS has low visibility into fine-grained routine runtime memory behavior information. As a result, it becomes challenging to make timely decisions based on quickly changing memory access patterns or other dynamic behavior. Considering the key role that the virtual memory has in the overall performance of the modern systems, a wide body of research proposed mechanisms to alleviate the overheads associated with the conventional virtual memory framework. However, despite notable improvements, these solutions suffer from two major shortcomings. First, they are mainly designed based on specific system or workload characteristic and are applicable only to a limited set of applications or problems. And second, each solution requires specialized and not necessarily compatible changes to both the operating system and the hardware, which makes implementing these proposals at the same time in a system a daunting prospect. This highlights the need for a holistic solution to efficiently support modern application in today's diverse system configurations by eliminating the inefficiencies of the conventional virtual memory framework when handling today's applications' large amount of data, and exploiting the properties of different pieces of program data to improve performance, efficiency, and other metrics in the system. In response to the need for a holistic solution, our goal in VBI is to design an alternative virtual memory framework that has two properties. First, to efficiently and flexibly support the increasingly diverse data properties in modern applications, as well as the diverse system configurations that are designed to cater to such data demand. And second, provide the key features of the conventional virtual memory framework while eliminating its key inefficiencies when handling large amounts of data in modern applications. I will now describe the key idea and the guiding principles of the VBI framework. Considering the challenges that the conventional operating system managed virtual memory framework faces, the key idea in VBI is to delegate the physical memory allocation and address translation to a dedicated hardware in the memory controller. The VBI design is driven by three guiding principles. First, programs should be allowed to choose the size of their virtual address space. This mitigates the address translation overhead associated with unnecessarily large and fixed size virtual address spaces in current systems, which causes more and more inefficiencies with the diverse memory requirements of modern applications. Second, address translation should be decoupled from memory protection, as they are logically separate. This enables opportunities to remove address translation from the critical path of an access protection check and deferring the address translation until physical memory needs to be accessed. As a result, lowering the performance overhead of virtual memory when handling large amounts of data in modern applications. It also enables the flexibility of managing address translation and access protection using separate structures customized to their characteristics, which again helps with more efficient address translation mechanisms that reduce the overhead of processing large data volumes in modern applications. And the third guiding principle is that software should be allowed to communicate semantic information about application data to the hardware. As shown by prior work, and as we discussed earlier, conveying data semantics to the hardware helps hardware to exploit the rich properties of different pieces of data in modern applications, and as a result, manage the underlying resources more intelligently. I will now describe an
Sure,
overview of
Nasran.
the...
I have a question before the prior slide.
Sure.
I think from that slide, something that might be striking to people that are not familiar with VBI is the idea of breaking the protection, decoupling the protection that virtual memory provides, right, in current systems, with the address translation part also. So my question basically is, do you think that if you do this type of decoupling, would VBI be more vulnerable to attacks like SPECT, for example, or do you have a solution to cope with that?
Yeah, that's a great question. So VBI stores access permissions that are decoupled basically from the address transition or the mapping information in VBI in a per process table called CVT. If they refer to figure 4 in the paper, which we'll see soon in the presentation, the access permission information are stored in per process tables called CVT, which in nature they're similar to TLBs, but only store access permission information for only the parts of data that that application requires to access, and the table is per process. It's a small table that in our case is like directly cached to the local CPU using a 64 entry direct map in our experiment. So if you think about it, it's basically not different in nature than what's happening now, which means that we do not open new vulnerabilities to such attacks. And the potentials of this design in improving the security against these attacks is something that we need to look into. But we certainly do not open new vulnerabilities to such attacks.
Thanks a lot, Nasran.
Thank you. Yeah, now let's take a look at VBI and how we basically implement these guiding principles in the VBI framework. So this figure shows an overview of the VBI design compared to the conventional virtual memory framework. Now I will describe how VBI enables this key idea, which is delegating the address translation and memory allocation duties to a dedicated hardware in the memory controller. So VBI introduces a globally visible address space called the VBI address space, which consists of a large set of virtual blocks of different sizes from a set of predefined size classes. All the virtual blocks are visible to all processes running on the system, and processes map each semantically meaningful unit of information, such as a data structure or a shared library code, to a separate virtual block of appropriate size. The key idea of the VBI design is enabled by the fact that the globally visible VBI address space provides VBI with system-wide unique VBI addresses, which can be directly used to access on-chip caches without requiring address translation, which as a result, according to the key idea, the address translation and memory allocation can be deferred until necessary to access the physical memory. To this end, the address translation and physical memory allocation are delegated to the hardware-based memory translation layer in the memory controller. In VBI, the OS no longer needs to manage address translation and memory allocation for the physical memory devices. Instead, it retains full control over the access protection by controlling which program has access to which virtual block. In order to access a virtual block, a process needs to attach to that virtual block with the right permissions. To this end, the OS attaches the processes to their requested virtual blocks and stores the list of the virtual blocks attached to each process and their associated permissions in a per process table. OS performs access protection using this table to ensure that the process has enough permissions to access the requested virtual block. In contrast to the conventional virtual memory framework, where each process is mapped to a single fixed size virtual address space, irrespective of the actual memory requirements of the process, in VBI, any process can attach to any virtual block. Accordingly, the process's total virtual address space is defined by the set of virtual blocks that are attached to it. In other words, by the process's actual memory needs. This satisfies our first guiding principle. Furthermore, in contrast to the conventional design, where the OS manages both access protection and address mapping, VBI decouples the two by delegating the address mapping and translation to the memory translation layer, while allowing the OS to retain full control over access protection by controlling the mapping between the processes and the virtual blocks. This addresses our second guiding principle. And decoupling address translation and access protection allows VBI to maintain address translation information in separate structures than access protection, access permission information. This relaxes the constraint of sharing address translation structures with the OS, which exists in the conventional virtual memory frameworks. As a result, in contrast to the conventional frameworks, VBI enables the flexibility to employ different types of address translation structures that can be customized to the application's needs. Accordingly, VBI maintains a separate translation structure for each virtual block and can customize it to suit the properties of the specific virtual block that is assigned to. For example, single-level tables for small virtual blocks or those with many large contiguously allocated regions. Each virtual block in VBI is associated with a set of information, including a bit vector that indicates the semantic and access properties of the virtual block's content, such as access pattern, latency, or bandwidth sensitivity. This is the part that actually can sort information, metadata regarding what you mentioned, Geraldo, about processing in memory, data that is going to be used in the processing in memory part of the computation. The properties bit vector associated with each virtual block enables VBI to implement the third guiding principle by communicating the memory requirements and semantics of the data that the virtual block contains to the hardware. I invite you to refer to our paper for more information, including a detailed reference implementation and microarchitecture of VBI. I will now I actually would like to go back to this figure to show the CVT tables that I mentioned that are stored in the main memory and cached in the per process table for each CPU, which is basically just something similar to what TLB does, but only contains a permission information, and the granularity of storing that information is per virtual block, which is a higher granularity than page granularity that the current TLBs use to store permission information, which this actually has a positive impact on reducing the lookup overhead for this table, which is required for every memory access that happens in VBI.
So Nasser, while you are in that figure, I have some questions about the general idea of VBI. So the first one is like here we have the memory controller, right? And inside the memory controller implement the MTL. So how would that work if you have multiple memory controllers, for example? Does each one has a different MTL, or how it works, or they are shared?
Yeah, that's a great question. So we assume that every memory translation layer, every memory controller in the system has a memory translation layer, basically, no matter how many memory controllers we have in the system. And while there are many ways to implement VBI in system that has multiple memory controllers, our initial approach that we also discuss in the paper is to partition the available virtual blocks between multiple memory translation layers, or basically different memory controllers. So the virtual blocks that are in the system, this basically would mean that the higher bits of the higher order bits of the VBI ID, the VBID, will indicate the home memory translation layer of the virtual block. So in this scenario, each memory translation layer will basically manage the physical memory allocation and virtual to physical address translation for the set of virtual blocks that map to the region of the physical memory that is basically under the control of that memory controller. And processes have access to the entire physical address space, just like any conventional system, and can allocate memory in any region of the memory, regardless of which memory translation layer manages that region of the physical memory. So the properties associated with a virtual block allocation request and also the availability of a free physical memory region at each memory translation layer are considered when we are going to allocate memory for each of the processes. We basically decide which memory translation layer to choose to allocate physical memory from the region that's under its control. There are more details regarding that multi-node basically systems in the paper. I hope that answers your question.
Yes, thank you so much. I have a second one. So is there any notion of memory defragmentation or garbage collection in VBI?
Yeah, so the difference between VBI and the conventional system is that we have the memory transition layer now in the memory controller, that we envision it as a software running on a programmable low power core within the memory controller. So as a result, if you think about it, VBI provides flexibility by making the memory transition layer programmable, and that allows to implement different memory management policies, such as garbage collection or defragmentation, also address translation that I explained in the presentation as well. So VBI potentially provides us with an extra level of flexibility to implement, different garbage collection or defragmentation mechanisms for different parts of the memory or different pieces of application data that may not be, this flexibility may not be available currently, or be available at a higher cost in the current systems, conventional systems.
So much, Nasser.
Sure. There is a set of optimizations that VBI enables, and I will quickly go over some of them. So VBI naturally enables a variety of important optimizations, which are not, some of them are not easily attainable in conventional virtual memory frameworks. We discussed 7 examples of such optimizations in the paper, 3 of which are already achieved through our guiding principles, which I covered. I will explain 3 other examples of the optimizations now, and I invite everyone to read our paper to read more about 1 other example of optimizations that VBI enables, which is early memory reservation mechanism. Let's take a look at the first example optimization, which is inherently virtual caches. So a common approach to address on-chip caches in the conventional framework is virtually indexed physically tagged caches. In this approach, the core issues virtual address to the cache, while the physical address is retrieved by accessing the TLB in parallel to the cache index probe. In case of a TLB hit, the physical address is used to perform the tag lookup. And in case of a TLB miss, a page walk is required to retrieve the physical address required to access the cache. In order to remove the overhead of address translation for cache accesses, virtually indexed, virtually tagged caches access the cache using the virtual addresses only, without requiring address translation, and the address translation is performed prior to accessing physical memory. As a result, VIVT caches, or virtually indexed, virtually tagged caches, reduce the address translation overhead by reducing the number of address translation requests that are required. However, most modern architectures do not support VIVT caches due to 2 main reasons. First, since virtual addresses are not globally unique in conventional systems, VIVT caches suffer from synonyms and homonyms. And second, although address translation is not required to access VIVT caches, the access permission check required prior to the cache access still requires accessing the TLB and can induce a page table walk on the TLB miss. This is due to the fact that the protection bits are stored as part of the page table's entry for each page in the current system. And this is what VBI basically tries to address. VBI addresses both these issues. First, VBI accesses all on-chip caches using VBI addresses. And since VBI addresses are unique system-wide, they eliminate the possibility of synonyms and homonyms. And second, VBI decouples protection checks from address translation by basically storing them at in different structures. So what happens is that we basically conclude that VBI reduces the address translation overhead by naturally enabling virtual caches without their known complexities in current systems. I will now describe the second optimization example. As I mentioned earlier, in virtually tagged physically indexed caches, the physical address is required to access the cache, which needs the data to be already mapped and allocated in the physical memory. On a cache miss, then, the actual cache line is looked up and returned to the cache. In VBI, in contrast, All on-chip caches are inherently virtual and are directly accessed using the system-wide unique VBI addresses without requiring address translation. As a result, the physical address is not needed to access the cache, and also the cache line does not need to be mapped and allocated in the physical memory prior to being accessed in the cache. VBI exploits this opportunity and delays the allocation of physical memory for virtual blocks until it is necessary. Accordingly, on a cache miss, if MTL realizes that there's no memory allocated for the requested cache line, it simply returns a zero cache line. In this mechanism, the memory allocation for the virtual block happens when the first dirty cache line of that virtual block is written back to the memory. On the write back, the MTL defines the VBI address to physical address mapping for the virtual block and allocates the VB in the physical memory, the virtual block in the physical memory. The delayed physical memory allocation provides VBI with many benefits that are not easily possible in the conventional virtual memory frameworks. First, it eliminates the address translation for accesses to the regions that are not yet allocated, which reduces the address translation overhead of the system. And second, it eliminates the original memory request from accessing the memory as well by returning a zero cache line for accesses to regions with no memory allocation, which results in improving the overall system performance. And finally, it avoids allocating memory for smaller virtual blocks that may never leave the cache during their lifetime, which reduces the memory footprint of the process. As a result, by enabling delayed physical memory allocation, VBI reduces the address translation overhead, improves the overall system performance, and reduces the total memory consumption of the program. Let's take a look at the third example, optimization. As I mentioned earlier, the conventional virtual memory framework suffers from two-dimensional page walks where both guest and the host OS perform address translation. VBI, however, resolves this issue. In VBI, the guest OS and the host OS interact once to attach the process running on the virtual machine to its virtual blocks. Once attached, any memory access from the virtual machine directly uses the VBI address to access the caches, and the address translation is performed only at the memory translation layer in the memory controller. So directly, as a result of that, unlike the existing systems, address translation for a virtual machine under VBI is no different from that for a host. As a result, by eliminating two-dimensional page walks, VBI reduces address translation overhead in virtualized environments. Let's discuss the methodology that we use for testing VBI and evaluating our mechanism. For evaluations, we use a heavily customized version of RAM Layer to faithfully model all components of the memory subsystem, including TLBs and page tables. We have released this modified version of RAM Layer as well. Our workloads consists of benchmarks from Spec 2006, Spec 2017, Tailbench, and Graph 500. And here is a summary of the main parameters of our simulations. Let's take a look at the results. So we evaluate VBI for two concrete use cases. In the first use case, we evaluate how VBI reduces address translation overheads in a native and virtualized environments. We evaluate the performance of 7 baseline systems and 3 different VBI configurations. Here we present results for 3 baselines and 1 VBI configurations, and for the rest of the results, please refer to our paper. The baselines that we present here in this presentation are native, where applications run natively on an x86 system, virtual, where applications run inside the virtual machine, and perfect TLB, which is an unrealistic version of native with no address translation overhead. We also show results for VBI full, which is VBI with all 7 optimizations that I mentioned earlier. This figure compares the performance of virtual, VBI full, and perfect TLB systems normalized to the native system. Based on this figure, we make 6 observations. First, virtual reduces performance for 44 times on average compared to native due to the two-dimensional page table walks issue that is in the conventional framework. Second, perfect TLB improves the performance compared to native by 1.9 times on average by removing the address translation overhead completely. Third, VBI full improves the performance by 2.4 times on average compared to native by enabling all 7 optimizations that we mentioned earlier. And fourth, VBI full improves the performance by 4.3 times on average compared to virtual. This is basically due to the fact that in contrast to the conventional frameworks in VBI, the address translation overhead for the processes running inside the virtual machine is not different than the processes running natively on the system. And as a result, VBI enables significant performance improvements in virtualized environments, which is not available in the conventional virtual memory frameworks. The fifth observation is that VBI outperforms the perfect TLB system by 49% on average. This is also due to the fact that the benefit of VBI and optimizations that it enables is not limited to only reducing the address translation overhead. The delayed physical memory allocation mechanism reduces the overall system performance, as I mentioned earlier, by reducing the traffic to the main memory. I invite you to read more about why we can outperform the perfect TLB with VBI full system configuration. We make the conclusion that VBI can significantly improve performance in both native execution and virtual machine environments. For the second use case, we evaluate the benefits that VBI offers in harnessing the full potential of heterogeneous memory architectures, which are tightly dependent on the data mapping and migration. To this end, we evaluate a hybrid PC-DRAM memory architecture, and we examine 3 different system configurations. Hotness unaware PC-DRAM, which is a mapping mechanism that is unaware of the data hotness. The next one is VBI PC-DRAM, where VBI maps and migrates frequently access VBs to the DRAM as the fast memory. And the third system is ideal, that is an unrealistic perfect mapping mechanism, which uses Oracle knowledge to always map frequently access data to the DRAM. So this figure compares the performance of PC-DRAM and ideal normalized to the hotness unaware PC-DRAM. So as you can see, VBI PC-DRAM improves performance by 33% on average compared to the hotness unaware PC-DRAM by accurately mapping the frequently accessed data structures to the low latency DRAM. We observe similar benefits when using VBI in system with tiered latency DRAM, which is another heterogeneous memory architecture. And I invite you to go to the paper for more details and results, evaluation results for that experiment as well. We conclude that VBI is effective for enabling efficient data mapping and migration in heterogeneous memory systems by conveying the data semantics to the hardware and also enabling more intelligent management of memory resources as a result of that. Something that is not possible, this is basically something that's not possible in the conventional virtual memory frameworks, to convey semantic information about the data and to exploit that for making intelligent decisions in the system. I will conclude the VBI portion of my presentation by going through.
Nasser, before you conclude,
sure.
I have a question. Actually, 2 questions. So, for example, regarding SimDRAM flexibility, if a new workload comes tomorrow and needs a VBI size that is not supported by the hardware, how would VBI handle that? Is there any clear solution for that, or do you over provision for the amount of possible VBI size that might appear? Did you thought about it?
That's a great question. Yeah, the answer is yes. So as I explained earlier, VBI basically chooses the smallest available virtual block size that fits the piece of data that the program needs to allocate. And if the available virtual block sizes, size classes are larger than the requirements of the newly introduced workload, what we can do is it basically would directly result in internal fragmentation. But what VBI does to avoid the fragmentation in physical memory is that it takes two of its mechanisms basically help with that. First is that VBI can use a sparse translation structure to map the virtual block to physical memory so that the unused version of the virtual block can be paged out if required, right? And also the second one is that the early reservation mechanism that I mentioned that anyone interested can go to the paper to read more about, is that it helps utilizing the unused region of a virtual block to allocate other virtual blocks if needed. So the way that it works is that when you want to program wants to allocate a virtual block, if there's enough contiguous physical memory available at that moment, we will assume that we reserve that contiguous region of physical memory for that virtual block and consider it a directly mapped virtual block. But the difference with direct mapping is that the reserved areas are available for other programs or other processes to allocate their virtual blocks in if required, or in other words, if you run out of physical memory. So the allocation can be basically split among smaller VBs with the same permission and properties using the early reservation mechanism. So what I explained is possible in VBI using the MTL and the CVT, that in a way that they can perform the multiple virtual block allocation transparently from the processes in case the virtual block size classes are too small for the virtual block that we need. We'll allocate it using multiple smaller virtual blocks with the same permissions and properties, and memory transition layer and the CVT tables that I mentioned will take care of transparently handling that transparently from the programmer point of view. So I guess I covered both cases of if there's not a size class that fits the virtual block size that we need.
So much. That is very clear, Nasran. My second question is about evaluation. You said that you use Ramulator for your evaluations, and a version that I guess is online and available for people to is in Safari's GitHub repository, I suppose.
It is going to be like it was available at some point, and there's some maintenance happening at the moment, but it will be available again soon.
That is great. That is great.
Yeah.
So
at the Safari GitHub.
Great. So my question is to the aftermath. Have you considered implementing VBI in a real operating system, and would be too challenged to do? Like, do you foresee challenges of implementing such a proposal in a real system?
Yeah, so it is basically not like straightforward to implement a framework like VBI in the OS, in a real OS at the moment, because it requires hardware changes. It requires the memory transition layer, right, to operate. So it is not easily possible to implement it without basically prototyping the memory transition layer. But to make up for that and to make sure basically that we do not ignore any important issue, we try to figure out what happens in every scenario for important and key tasks that happen in the OS. So if you go to the paper, we have cases such as the copy on write, or how the system boot happens, how the process creation happens, and sharing and shared libraries, or different scenarios that OS, which basically relate to the key tasks that OS is responsible for. So we explain how these happen in VBI under a VBI framework. But to practically implement them, we need to prototype the memory transition layer, which is something that we have in mind.
Thanks so much. This might be a fun future work for us, I guess, or someone else that is interested. So I don't have any other questions. Thanks so much, Nasran.
Of course. So yeah, we in this talk we introduced the virtual block interface, which is a new virtual memory framework to address the challenges in adapting conventional virtual memory to increasingly diverse system configurations, and also the high data demand in modern applications. The key idea of VBI is to delegate memory management to the hardware in the memory controller, and the memory controller-based memory management in VBI leads to many benefits not easily attainable in existing virtual memories, such as inherently virtual caches and avoiding two-dimensional page walks in virtual machines. We experimentally showed that first, VBI significantly reduces the overheads of address translation by reducing the number of translation requests and also associated memory accesses. And second, it increases the effectiveness of managing heterogeneous main memory architectures. We conclude that VBI is a promising new virtual memory framework that can enable several important optimizations and increase the design flexibility for virtual memory. We believe and hope that VBI will open up a new direction and many opportunities for future work in novel virtual memory frameworks. Great, so at this point, we have covered SimDRAM and VBI, the data-centric and data-aware approaches that we have introduced for efficient data handling in modern computing systems. And I will conclude this presentation and briefly describe the future research directions. So we conclude that efficient data handling in modern computing systems can be enabled using new frameworks that are developed based on a fundamental rethinking of computing paradigms and also key concepts of the key concepts and components in the modern computing systems, with the goal to make them data-centric and data-aware. So in this seminar, we showed that the overall performance and efficiency of the system can improve significantly using data-centric architectures that minimize data movement and compute data in or near where the data resides. And also data-aware frameworks that understand what can be done with and to each piece of data and make use of different properties of data to improve performance, efficiency, and also other important metrics in the system. So as future directions, I believe that this study, the study that led to the works that I presented in this presentation, opened up many new research directions and opportunities. Here I describe two major future directions, which I believe the ideas and approaches presented in these two works can be extended to tackle other issues in modern computing systems regarding the efficient handling of large amount of data in modern applications. So as we showed earlier, conveying the properties of different pieces of program data to the hardware can enable significant performance optimizations. We believe that data-aware memories, or in other words, memory architectures that understand and exploit the properties of the data to make intelligent utilization decisions, can significantly transform the computing landscape by basically exploiting information that was previously unavailable to the memory in an easy and flexible manner now using frameworks such as VBI. And the native support for conveying data properties to the hardware in VBI can enable a wide range of research and development in this area, serving basically as a platform to demonstrate many data-aware hardware optimizations in main memory management. So the second direction is regarding the virtual memory support for processing using memory architectures, which relates to basically our first work, which is SimDRAM. The full adoption of processing using memory solutions such as SimDRAM requires support for key virtual memory functionalities. More specifically, relying on the CPU to provide the processing using memory architectures with address translation and memory allocation can potentially nullify the very benefit of the processing using memory approach, which aims to reduce the interaction between the main memory and the CPU. Accordingly, designing efficient support in processing using memory architectures for critical virtual memory functionalities such as address translation and memory allocation is a promising research direction in our opinion. Thank you for listening to my talk, and I'd be happy to answer your questions.
Hi, Nastan. This is Nika. Thank you for your talk. Nastan, I was wondering if SimDRAM requires specific error correction mechanisms, and how would the reliability of SimDRAM operations basically be supported with conventional error correction mechanisms, or whether it needs a specific support in addition to that?
Yeah, that's a great question. So in our evaluations in the paper, we assume that triple row activation, which is required to perform the majority operation in SimDRAM, is absolutely reliable. But then what we show, as we show in our reliability evaluation, which is section 6.1, I think, in the paper, a triple row activation can fail depending on the amount of manufacturing process variation that we observe in the basically processor. So since in the memory, so since SimDRAM operations are executed within a DRAM module, it is very challenging to leverage existing DRAM error correction and mechanisms which typically perform correction at the CPU side of the memory in conventional systems. The same problem also exists for any other in-DRAM computation mechanism that operates directly on the data values stored in the DRAM cells. So this is something that applies to any in-DRAM computation framework, not only SimDRAM, and investigating it requires its own, paper, I would say. So does it
Thanks
answer
a
your
lot,
question?
Nasta. Yeah, thanks.
Sure.
So I have a question about the future directions that you talk about.
Mm-hmm.
So if you, I have two questions actually. So the first one for SimDRAM, because it's closer to my heart.
And you're also a co-first author on?
Yes. So what do you think that is the next step for that work? Or like, what is the main limiter of the SimDRAM proposal in a high level, of course, that you think that needs to be solved to fully enable processing using DRAM, if any?
Yeah, that's a great question. So there is actually, as you know, and I would like to explain it to others. Let me share this screen actually. Do you see my slide?
Yes.
Yeah, so there are three key limitations to the current example implementation of SimDRAM that we presented in the paper. So these are basically what I think, if address would make it a much more comprehensive framework for computation in memory. So the first one is that floating point operations. So at the moment, SimDRAM supports only integer and fixed point operations. The problem is that enabling floating point operations in DRAM while maintaining low area overhead is a great challenge, because floating point addition requires shifting the mantissa, for example, by the difference of the exponents of the elements. And because each bit line in SimDRAM stores a data element, shifting the values stored in one bit line without compromising the values stored in the other bit lines at low cost is currently infeasible. So being able to perform floating point operations would be great addition to SimDRAM, which is not available at the moment in the example implementation that is present in the paper. So the next one is that SimDRAM has issues with the operations that require shifting data across bit lines. So different prior works basically show that while different prior works do present some designs that may make it possible, basically. SimDRAM does not add any extra circuitry to perform bit shift operations. Instead, as I explained, SimDRAM stores data in a vertical layout and can perform explicit bit shift operations if it is required by orchestrating row copies. So even though this approach enables SimDRAM to implement a large range of operation, it is not possible to perform shuffling and reduction operation across bit lines without the inclusion of dedicated bit shifting circuitry, which is available in some prior work. So this is basically due to the lack of physical connection across bit lines that is present in the SimDRAM implementation that is present in the paper, which can be solved by building a bit shift engine near the sense amplifiers. The reason that we don't have, we basically try to stick to the subarray organization as it is without any extra circuitry on top of what, for example, Ambit requires to enable in-DRAM computation. This limitation is a result of that. So adding a bit shift engine near the sense amplifier would address this issue. And also the third limitation is synchronization between concurrent in-DRAM operations. So SimDRAM can be modified to enable concurrent execution of different operations across different subarrays in DRAM, but this would require the implementation of software or hardware synchronization primitives to basically manage the computation of a single task across different subarrays. This is not currently available in the implementation that is in the paper. But I would say these three limitations, if addressed, would make it a comprehensive enough framework or an improvement on top of the framework that SimDRAM is at the moment.
So much, Nasser, on that answer one of my questions. We have a question from YouTube. Someone is asking, do you think SimDRAM ISA can be extended to mitigate rowhammer?
So that's a great question. Many of, actually not any, but many of the IndiRAM computation frameworks that are similar to SimDRAM, which basically need specific rows in the DRAM subarray to perform computation, are vulnerable to rowhammer attacks because they basically need a specific rows to be accessed over and over again to to basically perform the computation. So what can happen is that this is not, as I said, something specific to SimDRAM, but there are mechanisms, general mechanisms that are to address rowhammer issue are orthogonal to our proposal, and they can be applied to SimDRAM or any IndiRAM computation mechanism that uses specific rows in the DRAM to perform computations. So what is there is that we do not open new vulnerabilities to rowhammer attacks on top of what other IndiRAM computation mechanisms frameworks do. And if we can improve it or not, that's a question. But certainly rowhammer prevention or prevention mechanisms are applicable to SimDRAM framework as well.
Thanks so much, Nasser. We have a comment on also in YouTube that says, nice presentation and very ground-breaking research work. Thanks, Dr. Nasser. So thanks, Dr. Nasser. And my other question was about, is more like a open question. Like you talk about data intelligent or data aware architectures doing your thesis and doing this talk. You talk about SimDRAM, like more related to making the memory more intelligent, and VBI is more related to make the system more aware of the data that it's using. What else is there? Do you think there is some other place that we can make this data-centric, or to enable more communication across the elements of the system, like, I don't know, maybe in the ISA or something like that?
Well, other than the, I need to go, I like to go one step higher, as in terms of like go a higher level and answer that question in a higher level. So as you mentioned, I cover data-centric and data-aware are approaches to handle data efficiently in modern systems. But a third direction that I think is worth looking into is data-driven approaches, which basically would be approaches that take advantage of the amount of data, the large amount of data, to improve the policies of the management policies in the system, software or hardware policies. So what I mean by that is that, as we said, there's a large volume of data being processed by the applications today. So why not we take advantage of the large volume of the data and learn the behavior of the application, because now we have a lot of data being processed and accessed. So why not we learn the behavior of how the data is being accessed or being processed, and take advantage of that knowledge to improve the performance of the overall performance of the system. So data-driven approaches is what it wasn't covered in this presentation, but I think is a very important direction to look into. I'm not sure if that answered your question.
It does answer. I was just wondering what was next in that broad aspect of the field. So thank you so much. Do we have any further question from the audience? I guess we don't have more questions from YouTube. I guess we don't have any. So I think this is we call it the day. Thank you so much for the great talk, Dr. Nasser.
Thank you, Gerald.
Thanks everyone for joining. And bye-bye.
Thank you, Nasser. Bye.
Thank you, Nika. Thanks for the question.